Here's a little solution video for motion worksheet 6, also known as assignment number 6. Mr. McGrath, that's me. So let's see what we got here. A dog runs west at a speed of 3 meters per second for 8 seconds. Now this is all constant velocity stuff here, so I'm just going to remind myself that displacement is equal to constant velocity times time, and sometimes we have the version of that where we write out plus initial position, and this is just like our position. In other words, you break up that delta x. For right now, I think this one's going to be helpful. So here, 3 meters per second, this is a v, and that's a time. So during this little span of 8 seconds, our doggy is going to go 24 meters, right? If you're going 3 meters for every second and you do that for 8 seconds, then that's 24 meters is the delta x. I'm just going to add that information in there. Stops and sniffs the ground for 5 seconds, then turns around and runs east. So turns around, got to be careful, and here are these directions, west and east. Those are opposite directions, so I'll have to deal with that. And runs 42 meters, that's a delta x, in 7 seconds. So let's see, delta x divided by time, if we do a little algebra there, the velocity is delta x over t, so for this little stretch, looks like the velocity is 6 meters per second, distance over time. All right. So let's see, what is the total distance traveled by the dog? Total distance doesn't care about what direction you're going, it just tracks the total distance that you've traveled, exactly like it sounds. So here I got 24 meters, and then I got 0 during this, because we're stopping. So 24 plus 0 plus 42 is, so that's like the 3 different things that happen. I'm just going to write them all out so we can really understand what we're doing here. Those are the 3 legs of the journey. So 66 meters total. What is the net displacement of the dog from the beginning to end? Well, displacement does care about direction. So I think for right now, I'm going to make this. I'll make a better version of this when I get to E for the motion map. But right now, I'm going to make a decision that west, I mean, you probably think about north, south, east, west. If you think about this like usual orientation of these things, then east is this way, which that feels more positive to me. This is an arbitrary decision, which means you could decide the other way. But what you do, what is not a choice, you have no choice in the matter about making one of these has to be positive and one has to be negative. They can't be the same sign, because that means the same direction. So I'm going to say that east is positive and west is negative, because that just makes more sense to me, like lining it up with number lines and math and stuff. All right, so what's the net displacement of the dog? Displacement does care about signs. So let's say he starts at 0, and then he goes 24 meters west. So that's to 24. I'm going to make that negative, like a number line. And then it goes east 42 from here. So negative 24 plus 42 is 18, right? And so that's where he ends up. So if my starting position here was 0, my ending position is 18, so my displacement is positive 18. Went from there to there. Or you could do displacement is equal to final position minus initial position, which is 18 minus 0, which is 18. Now you might be saying to yourself, okay, I get what you did there, Mr. McGrath, but What if I didn't start them at 0? Well, it wouldn't make any difference because this is the difference between them. So they would still be 18 apart here. So if you started the dog at, I don't know, anywhere else, you still should get this, whatever, the difference between those should still be 18. Right? So for example, if you started at 10, then all of these would be 10 bigger. And when you subtracted here, you'd still get 10, or 18 rather. Okay, what's the dog's average speed for the entire trip and average velocity for the entire trip? Well, once you have total distance and displacement, these are really easy to do, right? We've seen this before. That average speed is equal to total distance over time, and average velocity is displacement over time. And I have those numbers. They're right here. So total distance is 66 meters over what's the total time? Let's see, I got 8 seconds plus 5 seconds plus another 7 seconds, so total of 20. Notice that I do have to include this. It's part of the whole thing that happened. So that is, what's 66 divided by 20 is 3.3. Is the average speed, and the average velocity is interested in displacement, so that's 18 meters over 20 seconds, which is 0.9 meters per second. All right, sketch a motion map. I've kind of got a little head start on that here, so if we made this number line, this is 0, this is negative 24, and somewhere over here is 18. So the dog's going to go, I'll start here, and then for the first 8 seconds, we're going to go 3 meters per second. So, and this is 6 meters per second. So I guess if I wanted to scale this, I could do it by 3s. Let's see how good this looks. This is a little bit cluttered. You get the idea. Each one of these little tick marks is a 3. So 3, 6, 9, 12, 15, 18, 21, 24. And then in this direction, 3, 6, 9, 12, 15, 18. Okay, so for 8 seconds, I'm going to go 3 in the negative direction. Put my little arrows that go halfway. And then for 5 seconds, so this is time, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12. I'm running out of room. 13. 13. Right, to time 13, 8 plus 5. And there's 1, 2, 3, 4, 5 of those stacked up on the first one. If you're looking at this and you're like, wait a second, it says he's stopped for 5 seconds, and then there's 6 dots here. That's correct because time passing is in between dots, right? You don't get a whole second passing until you put the second dot there. So that's 1 second that passed. So having 6 there is correct. And then 6 meters per second for 7 seconds. So that's 2 dots worth, right? 1, 2, 3, 4, 5, 6, and 7. And then I'll make my little arrows that go halfway to the next dot. Great. Oops, one more, sorry. There we go, back to 18. Okay, so that's a little bit crammed in there. Sorry about that. That's what we're looking for. For this whole thing, if you decided that west was positive and that east was negative, that's fine. You would have this, except it would be flipped over, and that's totally fine. It's not right or wrong. You just have to be consistent with whatever you decide. Okay, sketch a position time graph. So I know I'm going to have positive and negative values. So I'm going to make my axis somewhere in the middle here. And I'm going to scale this. I think I'll scale it the same as what I did with my motion map. I'll go by 3. So this is like 3, 6, 9, 12, 15, 18, and then down to negative 24 there. And then here, same thing, 6, 12, 18, and I think I don't need to go more than that. And let's see, I have a total of 20 seconds. Do I have enough? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I don't have enough to do the whole 20 seconds. So I'm going to scale by 2s then. 2, 4, 6, 8 seconds. That's an important thing there. 10, 12, 14, 16, 18, and 20 would be here. So starting at 0, first leg of the journey is the going backwards. It takes 8 seconds to get to negative 24. Oh dear, sorry, that's supposed to be just one line there. Kind of missed my retracing. And the slope of this would be negative 3, right? The slope of this is the velocity. Then for the next 5 seconds, which is to time, that's 10, 12 to here. I'm going to stay there. And then I could sketch this by saying, okay, I know it's got a slope of 6, like over 1, up 6. But I think it's easier since I know that we get back to position 18 at time 20, right? So I think that's the easiest way to draw it. Make that dot, and I know that at constant velocity here, so everything's pieces of straight lines. So I think that's what that should look like. Again, if you decided that west was positive, it would be upside down. You would be like that instead, and that is perfectly fine. All right. A car is traveling on a highway at 80 kilometers per hour. I think on your copy of this, I think I fixed the units here. If I didn't, just take a look here. This should be in kilometers, and this should be in hours. I was not trying to make you convert to meters per second. That was not the idea here. It was just a mistake in the units. But I think maybe I fixed it before I sent it out to you. So a car's traveling on a highway at 80 kilometers per hour, and a truck's going 96 kilometers per hour in the same direction as the car. If the car starts out 40 kilometers ahead of the truck, okay, so they're going the same direction, nobody's going the other way, so I think that means that we can put our origin right down at the corner here, right, because everybody's going the same way. Car starts out 40 kilometers ahead of the truck, and both continue to travel at their given speeds. How long will it take the truck to catch the car? Show your work. Problem should be solved algebraically and graphically. So that means, I think I might have added in here somewhere also that I want you to write the position equation for both of them. And I think I'm going to do that first, because the thing about the graph is I could like pick some scales and work things out and make my graphs. But I'd kind of like to know where the intersection point's going to be so I can think about how I want to scale it based on that. You don't have to do things in the order that I'm going to do them, but that's what I would recommend, I guess. So here's the position equation for the car and the truck. So now what I'm thinking here is I'm thinking about position is equal to constant velocity times time plus initial position, plus the starting position. That's how you write the equation for one of these lines, right? So let's do it for the car first. What's the car's velocity? It is 80 kilometers per hour. That's this, times time. This is like your y equals mx plus, this is the starting position. That's like the intercept. The car starts out 40 kilometers ahead of the truck. So if I say the truck starts at 0, then the car is starting at position 40. Okay? So definitely thinking y equals mx plus b and understanding that these are the things that go in there. That's always going to be an x and a t. This the m slope here is your velocity, and the b is your starting position. All right, how about the position for the truck? Well, the truck's going 96 kilometers per hour times time plus, well, we gave the car the 40-kilometer head start from the truck, so the truck's starting position is just 0. So you could leave that off. It's just 0, but just want to write it in so we have the complete information there. Okay, I mean, you could totally graph these right now, right? But I don't know how I want to scale it until I can see where these intersect each other. So I'm going to do this first. I'm going to solve it algebraically. You have known since a long time ago in some math class or other how to do this, how to find where these two things intersect. You set them equal to each other. I want to know when and where they're at the same place. So how do I do that? I just set those two positions equal to each other. So I set this equal to this and I'm going to figure out the time first. When I start doing algebra, I'm not going to write down units anymore because it's a little too cluttered, in my opinion. So 80 t, these are the units that belong to that number. So I'm just dropping those for now, plus 40, again, I'm going to leave the units off, is equal to 96 t. And I subtract that over to the other side, and divide. So the time when the truck catches up to the car, it happens after 2.5 hours. Now, I would also like to know, so that gives me an idea maybe of how I want to scale this axis. I don't want to make this like 1 hour, 2 hours, because then it like happens really early in the graph, and I'd like to use more of the graph. All right, how about where do they intersect? That would happen, you can plug this 2.5 back into either one of these. So if I plug it back into this one, 2.5 times 80 is 200, so at 240. And you could also plug it into this one. You will get the same thing if you have the right time. So that gives me an idea how to scale this. And now it should be pretty easy to draw. Let's see how many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I don't have enough to go by tens. If I had a few more, I could do that. So let's go by 20s instead. So that'd be 40, 80, 120, 160. I'm just writing a few of them in there. 200, 240, and that's where they intersect. So I could stop there. You can keep going as far as you want. And then let's see. I got a bunch of room here, so maybe I will make these, if I thought about these as being like 10-minute intervals, or you could do like quarters of hours. I think I'll make them like 10-minute intervals. So this would be like 10, 20, 30, 40, 50, 60 minutes. So each 6 of those will be 1 hour. 1, 2, 3, 4, 5, 6. The scaling has to be evenly spread out. You can't put 1 here and then put 2 in some other place. That makes it wrong. 1, 2, 3, 4, 5, 6. For 3 hours, and that's enough time to see what happens here. Okay, so to make these 2 lines, you can do it like graphing by slope. Say, okay, if I go over 1, I have to go up 80 here. But if you know where they intersect and where they start, you have 2 points. So you could just graph the 2 points and then draw the line in. So I know that they intersect at time 2.5 hours and position 240. So as carefully as I can, double check that I've got the right spot there. That looks good. So their 2 lines should cross here. The truck starts at the origin. Sorry, the truck starts at position 0, we should say. And the car starts at position 40. And that looks pretty good. When the 2 things don't look like they intersect exactly where you want them to, just make the dot bigger. That's my secret there. So that looks great. All right. So solving algebraically and graphically, we really did more of the algebraically and then used our algebra to make the graph look just right. You could, if you made your graph very, very carefully and did your like, okay, I'm going to go over 1 hour and up 80 and so on, you could make you could find the intersection by doing it graphically. I think that's more difficult. It means your graph has to be super, super accurate. All right. So same thing. I think again I asked you to write the position equations for these runners, and these, if you read the description here, which I presume you have already done, they start 200 meters apart and they're running toward each other. So I think I already know something about my scaling here. And if this looks like a copy of the same blank graph here, so I think this is 20 high. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if they're 200 meters apart at the start, I'm going to call that 200 meters, and then I'll be scaling by tens. 1, 2, 3, 4. So that'd be 100 meters right there. And I don't know about the time yet, so maybe I'm going to try to do some, do a little math here. So let's see. 2 runners are 200 meters apart, and both are initially standing still. Runner A starts running toward runner B at a constant speed of 6. So now, which one is here and which one is here? Well, who's to say? I mean, you got to decide. I guess I'm going to make this runner A start here. But you could have done this the other way and started runner A here. It just depends, you know, on your... 2 people could be watching this from the opposite sides of where the runners are, and to one person it looks like runner A is going to the right, and to the other person it looks like they're going to the left. So it's really your choice. I'm going to go ahead and start runner A here toward runner B at a constant speed of 6. Okay, so this runner is going to be going in the positive direction, and runner B is going to be in the negative direction. So definitely one's going this way, one's going this way, right? Which means one of them, the velocity is going to be positive, sorry, pointing to this, and the other, the velocity is going to be negative. So let me try to write the position equation for runner A. If you did this, if you struggled with this one and things are making a little bit more sense after this, then you should pause the video here and try to work on this a little bit more yourself. It's a much more, you're going to learn a whole lot more about doing this than if you just kind of watch me do it and copy stuff down. All right, so welcome back. But no, seriously, pause and try it. Okay, so position of A is equal to the velocity of runner A is 6 meters per second times time, and I'm having runner A start here. All right, so they're going to go here and have a slope of 6, but I haven't decided about the scaling yet, so not sure how that's going to work. 3 seconds after runner A begins running, then runner B starts running toward A. So like 3 seconds later, they start running. How do you do that? That's going to be a little tricky. So the position of B is, I know that their velocity is -5 the other way at 5. But how do I do the intercept where they start? Because they start at 200, but they don't start at 200 until 3 seconds later. So there's 2 ways to do this. One thing, depending on how solid you feel about math stuff, you could say, okay, well, I want it to start at 200, but it's shifted over 3 seconds to the right. So you could do this. That's how you shift something to the right. And then start at 200. Or you could do, maybe the same slope either way. You could say, okay, well, where would the intercept be if I just kind of dialed this back? If this person is going 5 meters per second this way, like every second that goes by, their position goes down by 5, what would happen if you went backwards by 3 seconds? Think about that for a second. Well, if you go forward 1 second and it goes down by 5, if you go backwards, like they're never actually here, but if we wanted to write the equation for this, it's like they started at 215, right? Because you go back, up 5, back, up 5, back, up 5 more. So notice here that if you distribute this, -5 times -3 is +15, so these are the same. Either one of those will work. Okay, so I think I'm just going to scale this by 1 second. All right, so that would be here 5, 10, 15, 20, and so on. And you can either like work out the slopes here and plot everything, or you can do the algebra, set these two things equal to each other like we did here. I'm going to go ahead and do that, figure out where they cross, then I'll find that point and draw the lines. So here I've got 6t plus 0, setting the two positions equal to each other. I'm going to use this one because it's already distributed out. -5t plus 215. So it looks like I got 11t equals 215. So they're going to meet each other at time about 19.5 seconds. And it's going to happen at position. I can plug that into either one of these. I'll go ahead and plug it into that one. That's easy. Oh, at about 117 meters. Okay, so these are scaled by tens. So 117, this is 120. So almost up to that. And then this is almost to 20 seconds. 19.5 seconds. So about there. I'm not going to ever take points off you for not being like super exact in a graph. Just do your best. And then runner A starts here, and runner B starts 3 seconds later, right here. And I'm not going to draw that part in going backwards because that didn't really happen. It's just like where that runner would have been if we start their time at 0, if they had started at 0. All right, that's it.